Okay. Good afternoon, students. Can you hear me?
Yes, sir.
Okay, thank you. So, can you please tell me what we discussed in last week? So, so can you please tell me any both? I mean, any of you, what is KVL, what is KCL, what is Ohm's law? Just, I mean, it's a review kind of thing. Please tell me.
The algebraic sum of voltages is called equals to 0 KVL, sir. KCL means sum of entering currents is equal to sum of leaving currents at the node, sir.
Okay.
Ohm's law means it is the
Hmm.
product of resistance and current at constant temperature, sir. V is equal to
Okay.
IR at constant temperature.
Okay, fine. So, okay, I mean, so what else we discussed? Tell me. Suppose we are connecting resistors in series. What is the equivalent resistance?
R1 plus R2 and R1 plus and so on, sir.
Okay. So if they are connected in parallel,
1 by R1 plus 1 by R2 and so on 1 by Rn, sir.
okay. So what about inductors in series?
Inductance and series is L1 plus L2 plus and so on, sir. In parallel,
Induct
1 by L1 plus 1 by L2 plus and so on, sir.
okay.
For capacitors in series, 1 by C1 plus 1 by C2 plus and so on, sir.
Okay.
For parallel, C1 plus C2 plus C3 and so on, sir.
Okay. Very good. Very good. So I mean, what about source transformation technique?
Voltage to current or current to voltage.
Okay. So I mean, strictly speaking, voltage source in series with resistance is transformed to current source in parallel with the same resistance. Okay.
Yes, sir.
So what is the I mean condition? I mean when we can't apply source transformation under what condition? So I told you. So the branches with some dependent variables. For those branches we can't apply source transformation technique.
Yes, sir.
Okay. So today we'll continue with the discussion. Okay. Let me share my screen.
Okay, sir.
So is my screen visible?
Yes, sir, it is visible, sir.
Okay. Thank you. So I told you already what are the types of different types of sources. Tell me. So the basic classification is independent source, then dependent source. In independent source, we are having voltage source and current source. So in voltage source, we are having ideal voltage source and practical voltage source. Similarly, in current source also, we are having ideal current source and practical current source. Okay, so that's about independent sources. So the dependent source, we are having again set of. I mean, we are having the dependent sources are classified into voltage control voltage source, voltage control current source, current control voltage source, and current control current source. Okay. Now tell me what is the basic difference between ideal and practical voltage source? We'll see independent ideal voltage source. Okay. I mean I told you already last week.
Axial means
No
no
resistance.
resistance.
Okay. So whatever the input voltage we are getting the same voltage as a output. Okay. So
Yes.
there is no voltage drop in between. I mean input and output. Okay. So
Yes.
those kind of voltage sources are the independent ideal voltage sources. Okay. That is what is shown here. I mean the output voltage V is equal to Vs constant. Why? Because there is no I mean passive element here. If there is some passive element, there will be some voltage drop across that passive element. Okay. So whatever the input voltage we are getting the same voltage as output. So the such kind of source is nothing but ideal voltage source. Okay. That is V is equal to Vs for all I. Okay. So I mean, so if you see here, note point, all these sources are inherently non-linear. Okay. Since in general for sources, the V and I relationship is non-linear. That's why Inherently, all sources are non-linear in nature. The reason is for sources the relationship between voltage and current is in general it is non-linear. Okay, that's why if it is non-linear, we can say they are active. So I mean active elements, and also we can say they are unilateral elements. Yes or no, students?
Yes, sir.
If the element is non-linear, we can directly say they are active elements and also they are unilateral elements. Okay.
Yes, sir.
Okay. Since the relationship is non-linear, it won't satisfy in bilateral condition and also it won't satisfy passive condition. So that's why non-linear elements they are active and unilateral elements. Okay. So when it comes to practical voltage source, so please look at here what is the difference. So students don't think that this is opened. Already some we are connecting one voltmeter or something like this here. Okay, don't say sir it is open. That's why the current flow is zero. Okay, that is wrong. So here we are connecting some meter here. Okay, we are applying voltage. So voltage Vs here, that is plus minus, and also we are having some resistance. Okay, so students, the circuits which we are discussing, in those circuits we are using only practical voltage sources and practical current sources. Why? Because there is no that much use with ideal voltage source or ideal current source. Why? Because so ideal means whatever the input we are giving, we are getting the same as the output. Okay, there is no there is no application in general with ideal voltage sources or ideal current sources. Okay, so if you see here, we are applying voltage Vs here. So there is some voltage drop across Rs, that is source resistance, we can say. So by using Ohm's law, tell me what is the voltage here? V is equal to I into R. Yes or no?
Yes, sir.
Okay. So now here the output side, that is plus minus V. That is we are going to find this output voltage. So to find this output voltage, what we need, we have to apply KVL across this loop. Okay, apply KVL. Tell me KVL equation. Students, please. Minus to plus means plus or minus.
సార్ ఒకసారి మళ్ళీ అడగరా సార్, వినిపించలేదు.
Okay, I'm sorry. So here, to get this output voltage, what we have to do, we have to apply KVL.
KVL, yes sir.
Okay. Okay, now apply KVL and tell me KVL equation. Minus to plus.
మైనస్
Minus to plus. Minus to plus.
ప్లస్ విఎస్ మైనస్ ఐ ఆర్ఎస్
Okay.
మైనస్ వి
Is equal to 0. Okay.
Yes,
So
yes, sir.
I told you in the last week. So in general, myself I prefer minus to plus. If the current direction is from minus to plus, I prefer the plus sign. If the current direction is from plus to minus, I prefer minus sign. Okay, you can do it the other way also. Okay. So if you follow minus to plus, minus sign means for plus to minus you have to follow plus sign. Okay, that is your choice, but you should not follow same sign for both, like minus to plus plus sign and also plus to minus plus sign. That is wrong. Okay. Okay, here we used passive element R. The voltage is IR, current is I is equal to V by R. Now if you see here, after applying KVL, Vs minus I into Rs plus to minus, that is minus V is equal to 0. Now the output voltage V is equal to Vs minus I into Rs. If it is ideal voltage source, V is equal to Vs. Since this is practical voltage source, V is not equal to Vs, but V is equal to Vs minus the voltage drop across the resistor. That is V is equal to Vs minus I into Rs. That's why if you see this figure here, so this is for ideal case, V is equal to Vs, but when it comes to practical case, V is not equal to Vs, but V is equal to Vs minus I into Rs. This is for ideal case, this is for practical case. Okay. So you can also note this point in practical voltage source, the terminal voltage, that is the output voltage, is function of current. Okay. So when I becomes 0, what happens? When I becomes 0, then again it acts as V is equal to Vs. That is, when I becomes 0, the practical voltage source acts as ideal voltage source. Why? Because when I becomes 0, the voltage across this resistor becomes 0 by using Ohm's law. So that's why the terminal voltage or load voltage or output voltage, that is V is equal to again Vs only. Okay. Is it okay? Shall I proceed? Okay, next, ideal current source. So, okay, here what is the condition? So, when you measure current here, okay, this is the input current. When you measure current here, that will be equal to the input current. Okay, that is I is equal to IS. Okay, that is what is you can say. The other way IL, that is load current or output current or simply the current I. Okay, so I is equal to IS. So for ideal current source, the current flowing through this load is equal to the applied current. Here the applied current, or you can say other way source current. Okay, so the current flowing through load, that I is equal to IS. Then we can say why, because here why we are calling it as ideal, because there is no division of current from input to output. Whatever the current we are getting giving at the input, the same current we are getting at the output. That's why this source is known as ideal current source. So if you see VI relation, I is equal to IS. Okay, so I is equal to IS for all V. Okay, next. So terminal current is independent of the terminal voltage. So why? Because here, whatever the voltage you apply, the current flowing through this voltage, this load is nothing but the input current. That is why we are saying the terminal current is independent of the terminal voltage. Why? Because there is no change here. Why? Because whatever the voltage you apply, the current remains same. In that way, we are saying the terminal current I, or you can say IL, that is independent of the terminal voltage V. Okay, this is about ideal current source. So next. Students, please tell me whether you are taking notes or not. You are just listening to me.
Sir, taking, sir.
So then you can. No.
Yes, sir. I'm writing notes, sir.
Okay. In that case, just tell me. Whether I am going a bit faster, because why? Because I am sliding down. That's why.
Okay, sir. Okay, sir. 5 minutes, sir. రాసుకుని చెప్తాను సార్ మరి.
Okay. Okay. Or else I'll do one thing. I'll share this PDF to you, anyways. Okay. Hello.
Okay, sir. Okay, sir.
Okay. Just listen to me clearly. If you're having any doubts, please try to ask me. Okay.
Okay, sir.
I will share this. Don't worry about this. Okay.
Okay, sir.
Okay. So this is about ideal voltage, so ideal current source. Next, we will see practical current source. Okay. Here, the practical current source means we are having, the current source in parallel with some resistance. Here we are measuring the current, that is terminal current or load current. Okay. So now what we have to do to find this terminal current, we have to apply KCL at this point. So if you apply voltage here, terminal voltage V here, what is the current flowing through this element? Tell me by using Ohm's law. You know voltage across this resistor. Now tell me what is the current flowing through this resistor by using Ohm's law?
I is
okay.
I is equal to V by R, sir.
I is equal to V by R. That IS is equal. You can say don't say IS. Something that I1. Let's say I1
Okay,
is equal to I1 is equal to V by RS.
Yes, sir.
The current flowing through this resistor RS is equal to V by RS. That V is the applied voltage, terminal voltage. RS is the resistance. Okay.
Okay, sir.
Now apply KCL here. Tell me the KCL equation. KCL at this node.
As it is entering, sir, minus IS.
Okay, very good.
The current is flowing from plus to minus, so it is.
No, not current. That is current direction leaving from the node.
Okay. Yes, sir. So leaving, so V by RS.
This is also
And
leaving.
it is also leaving, sir. I. Yes, sir.
Okay, very good. So this is entering. That's why this is minus IS. This current is leaving. That's why plus V by RS. This current is also leaving. That's why this is plus I is equal to 0. So when you express I is equal to IS minus V by RS. So if it is ideal current source, then I is equal to IS. There is no division of current. Okay. But when it comes to practical current source, I is not directly equal to is. I is equal to is
S
minus
minus
v
V by R.
Okay, if you see this graph, you can clearly observe this is a constant is for ideal current source. This is as you increase voltage, the current flowing through this resistor increases and the output current decreases. That's why this is going down. Okay, so here why? Because I is function of V. The terminal current is function of terminal voltage when you use practical current source. But when it comes to ideal current source, this I is independent of V. So there I is equal to Ix. Okay. So this is for ideal case, ideal current source. This is for practical current source. So now here you can see, so the terminal current is a function of terminal voltage for practical current source. There in practical voltage source, the terminal voltage is function of terminal current. So that is V is equal to Vs minus I into Rs there for the practical voltage source. For practical current source, I is equal to Is minus V by Rs. Here I is function of V, there V is function of I. Now when this voltage is equal to 0, when terminal voltage V is equal to 0, what happens? Voltage 0 means short circuit. Please remember, students, voltage 0 means short circuit, current 0 means open circuit. So we are making terminal voltage 0 means short circuit. Now tell me, what is the voltage across this resistor? When this is shorted, what is the voltage across this resistor?
0.
Why? Because parallel element, the resistor is in parallel with the short circuit. That's why the voltage across the resistor also 0. When voltage across the resistor is 0, then you can say the current flowing through that is 0. Why? Because I is equal to V by Rs, where V is equal to 0, I is equal to 0. Then, so when you make terminal voltage 0, the current source, the practical current source acts as the ideal current source. Yes or no? So you can remove this. Why? Because resistor Rs in series short circuit, the resistance is 0. Rs parallel with 0. Rs into 0 by 0 plus Rs, that becomes 0. I told you already how to combine two resistors in series. Tell me. I am giving two resistors R1 and R2 in parallel. How to combine them?
1 by R1 plus 1 by R2, sir.
You can say directly R equivalent is equal to R1 into
R1 R1 plus R2.
R1 plus R2. So in that way, you can combine these two. Then finally, it acts as a ideal current source when you make V is equal to 0. Okay. Shall I proceed?
Yes, sir.
Okay, thank you. Next, we'll see these sources are known as dependent sources, or you can say controlled sources. Why these sources are controlled sources? Because these are controlled by some variable. That variable is nothing but the dependent variable or controlled variable. Okay, so you can observe by looking at this plus minus sign. This is voltage source, arrow means current source, plus minus means voltage source, arrow means current source. Now tell me here, what is the dependent variable? Tell me first one. Look at the screen and tell me.
Voltage.
Voltage. Now tell me the name of this voltage source.
Voltage control voltage source.
Very good. So what is the variable here? Controlled variable?
Current, sir.
Source is current. What about variable?
Voltage, sir.
Now tell me what is the name of this source?
Current control voltage source.
No. This is current source, but it is controlled by voltage.
Okay, sir. Voltage control current source.
Very good, very good. This one, what is the source?
Voltage, sir, controlled by current source. Current control voltage source.
Very good. Last one.
Current control current source, sir.
This one, K1 into V1 square. This is also voltage current. This is I1 square. I'm sorry, I1 square. K1 into I1 square. Tell me.
Current control voltage source.
But it is non-linear. Why? Because here the variable is I1 square, which is non-linear. All these are linear control sources. This is non-linear control source. Why? Because the controlled variable or dependent variable is non-linear. You can say all these are linear dependent sources. This is non-linear dependent source. Okay. So when you can say the source is the controlled source is non-linear because when the dependent variable is non-linear in nature. Okay, that is I1 square, I2 square like that, or I1 cube. Okay.
Yes, sir.
The controlled sources are said to be sources, that is the active elements in the presence of at least one independent source. Then only controlled variables are non-zero. Okay, we can say so. Instead, the simply to say all these are sources only. Okay, you can say all these. I told you already. If it is rhombus shape, means that is controlled source or dependent source. Okay, so why it is dependent means it is depending on some variable. That variable may be current or voltage. Okay, when so this variable is non-zero, then only we can say this source, this controlled source is active. Yes or no? So we can't use directly this source in circuit or network. Why? Because this is depending on some variable. To find that variable, we need at least one independent source in the circuit. That independent source may be current source or voltage source. Why? Because the circuit with only dependent sources will not work. Why? Because there is no the dependent source is depending on some variable that may be current or voltage. Without having any independent source in the circuit, we cannot find that dependent variable. If you cannot find that dependent variable, there is no use with that dependent source. That's why the circuit with only dependent sources will not function. That acts as a dead circuit or dead network. Okay. In order to make circuit to function, we have to have at least one independent source. The independent source may be anything. It may be voltage source or it may be current source. So here, one more statement like the control sources basically linear. They are linear, active, and bilateral. So the presence of these elements makes the network linear, active, and bilateral. So since the control sources are linear, they are active and bilateral. So the presence of these, dependent sources in the circuit, then the circuit behaves as linear circuit and active circuit and bilateral circuit. Shall I proceed?
Yes, sir.
Thank you. So already we discussed these things. As you know, as a review, I am giving one more time. So it is defined at node case. KCL. I told you already. That is, we have to apply KCL corresponding to the node or junction, whereas KVL is corresponding to the loop or mesh. So the statement is like for KCL, the algebraic sum of currents at a given node is equal to 0, or the currents entering at the node, the sum of currents entering at the node is equal to the sum of currents leaving from the node. Okay. Okay. This is,
Okay, sir.
so now if you see here, tell me at this node what is the KCL equation?
I1 current entering, sir.
Okay.
So minus I1, I5 is leaving, so plus I5.
Okay.
And I4 is also leaving, so plus I4.
Okay.
I3 leaving, so plus I3, and I2 is entering, so minus I2, sir.
Okay, that is what is here. Okay, you can also express these two are entering. Sum of currents entering is equal to sum of currents
leaving currents.
These two are entering, these three are leaving. Sum of currents entering is equal to sum of currents leaving from the node or junction. That is important. Okay.
Okay, sir.
Now you can put here. So what is I is equal to dq by dt or not?
Yes, sir.
Substitute here. Tell me when you put I is equal to dq by dt. Tell me this equation.
dq1 by dt plus dqt by dt is equal to dq3 by dt plus dq4 by dt plus dq5 by dt, sir.
Now, so dt is common, na? Okay. Now tell me the I mean in terms of charge, you can move this. You can take out. You can take out of d by dt. Now tell me what is this equation?
q1 plus q2 is equal to q3 plus q4 plus q5, sir.
Okay, that is the charges corresponding to the entering currents is equal to the sum of charges corresponding to the entering currents is equal to the
Sum
sum of charges corresponding to
leaving,
the leaving current.
leaving current.
Okay, that is very simply the sum of entering charges is equal to the sum of leaving charges. Now tell me what is Q is equal to? If it is electron, N into E or not? Number of electrons into charge of that electron. Yes or no?
Yes, sir.
Okay, the charge of electron E is equal to 1.69 into 10 power minus 19 coulombs. Yes or no? Okay, so now you can write it as Q1 is equal to, tell me, Q1 is equal to the charge due to number of electrons N1, that is Q1 is equal to, tell me.
n1
Uh,
n1 n1e
uh,
plus n2e
is
is
equal
equal
to,
to n3e plus n4e plus n5e.
so the any E is common, pull it, pull out that. Then finally left with N1 plus N2 is equal to N3
n3
plus
plus
N4 plus N5. So sum of electrons corresponding to the entering currents is equal to sum of electrons corresponding to the leaving current.
leaving currents.
So simply to say, the sum of entering electrons is equal to the sum of leaving electrons. So the number of electrons entering into the node is equal to the number of electrons leaving from the node. See, so if you observe, these are the three ways, but our requirement is current. That's why we use only this definition. Okay, these are the three variants of KCL. Okay, but our requirement is, if you know this I, you can get these two. Okay, these two are from the, from this equation, that is I1 plus I2 is equal to I3 plus I4 plus I5. I is equal to dq by dt, q is equal to n into E. Okay, is it okay? Shall I proceed?
Yes, sir.
Okay, these are some of the features related to KCL. It applies only to the lumped electric circuits. I told you now already. Our networks which we are using in network analysis are networks. Those are all lumped circuits only. We can't use distributed circuits on paper. You may analyze, but practically you can't connect paper by showing some. Why? Because for distributed networks, we can't separate resistance, inductance, and capacitance. Okay, that's why the KCL applies to only any lumped circuit. It does not matter whether the circuit elements are linear, non-linear, active, passive, time varying, or time invariant. Okay, the circuit must be lumped. The lumped circuit may consist of any kind of element, like it may be linear element, non-linear element, passive element, active element. Okay, it may be time varying or time invariant element. Okay, for all those kind of the basic condition is the circuit must be lumped. Okay, the lumped circuit may consist of any element like linear, non-linear, passive, active, all those things. Okay.
Yes, sir.
Okay, next KVL. So KVL, I told you already, KVL corresponds to the loop or mesh. So the definition is algebraic sum of voltages inside a loop or mesh is equal to 0. Okay, so that is what is here. So see here and tell me what is the KVL equation.
V minus VR minus VL minus VC equal to 0, sir.
Okay, fine, that's okay. Now tell me what is, by using Ohm's law, what is VR is equal to?
I into R, sir.
What is VL is equal to?
L into di by dt, sir.
What is VC is equal to?
1 by C into integral I dt, sir.
Integral I dt. Since these are connected in series, the current flowing through these three elements is same. Okay. Now So if you have, when you apply KVL, V is equal to VR plus VL plus VC. The total applied voltage is divided across resistor, inductor, and capacitor. So that's why the applied voltage V is equal to VR plus VL plus VC. Now you know the voltage is defined as W by Q. That is W is the energy per charge. I mean V is equal to W by Q. I mean this is the definition of electric potential or voltage. Okay. Now substitute here. Tell me V is equal to W by Q.
W by Q equal to WR by Q plus WL by Q plus WC by Q.
So here what is common? Common is 1 by Q. You can take it out and now tell me the final expression.
W is equal to WR plus WL plus WC. Sir.
Total, this is the conservation of energy. Now there in KCL, that is conservation of charges. Okay, conservation of charges means the total charge that is coming from coming to the node is equal to total charge leaving from the node. Okay, at node, if you see clearly, the total charge is equal to 0. Okay, so see here, if you see inside any loop, okay, so the applied voltage is divided across these three elements. Inherently, we are speaking about energy corresponding to these three elements. Okay, that is W is equal to WR plus WL plus WC. KVL is independent of the nature of elements. I mean, even KCL also. There also we can say, we said the network should be lumped network. Okay, lumped circuit. The elements may be anything, active, passive. Okay, here also it is independent of nature of element. KVL expresses the conservation of energy. You can say energy in brackets power, conservation of power in every loop. Okay, so means within that loop, if we find power, okay, the power delivered is equal to the power absorbed. Okay, the same thing is hold true for the whole circuit. Okay, that's what I told you already. Each and every network or circuit, they must satisfy or they must verify Telegan's theorem. What is Telegan's theorem states? Total power delivered is equal to total power absorbed. Power delivered in a given circuit is equal to power absorbed in a given circuit. Otherwise, that is not a valid circuit. Each and every network or circuit, they must satisfy Telegan's theorem. Okay, shall I proceed?
Yes, sir.
Okay. So now from here, from KCL and KVL, by using Ohm's law, we can extend. KCL plus Ohm's law leads to the nodal analysis, and KVL plus Ohm's law leads to the mesh analysis. Okay, we'll discuss. I mean, there is nothing new in nodal and mesh. Okay, nodal is nothing but we know KCL, we know Ohm's law. When you use those two together, that is nothing but nodal analysis. We know already KVL and we know already Ohm's law. If you use these two together, that is nothing but the mesh analysis. So we may have some advanced version of nodal and mesh. That is, those are nothing but super node analysis and super mesh analysis. Okay, there also we use this KVL, KCL, and Ohm's law. So wherever Ohm's law comes into picture, there is one condition to be satisfied, that is at constant temperature. Whenever we are applying, we are using Ohm's law or we are stating Ohm's law means there the condition is the temperature must remains constant. At a constant temperature, we have to operate. There should not be any variation in temperature. Moreover, Kirchhoff's laws are independent of nature of elements. Okay, that is one more thing. And students, if you see here, the voltage KVL means Kirchhoff's voltage law. Voltage is across the element, and KCL, that is current is flowing through the element. So already I told you, voltage is across the element, current is flowing through element. Okay. So now students will see, now we'll move on to nodal analysis. Nodal analysis is nothing but the KCL plus Ohm's law. Okay. So I mean, in order to apply nodal analysis, what are the things we have to consider first means? So students, in GATE point of view or in the competitive examination point of view, I mean, whichever method is easy or whichever method is the best fit there, we have to use that method. Okay, why? Because there is no necessity that we have to use nodal or we have to use mesh analysis. But in my observation, nodal analysis is the nodal analysis gives you answer in short time compared to mesh analysis. Most of the cases. In some cases, mesh analysis gives you answer in less time compared to the nodal analysis. But in my observation, I use many times nodal only. Okay, maybe in some special cases or in very less cases, I use mesh analysis. Okay. To apply nodal analysis, we have to identify number of nodes in a given circuit. Node is nothing but a junction where there is some division of current or addition of currents will happen. Okay. So we have to identify number of nodes. Then after, and also we have to identify reference node also. Okay, so the total number of nodes in a given network is equal to the number of actual nodes plus reference node. So whenever we are applying nodal analysis means with reference to some ground or something we have to apply. Okay, that is what is these two are nodes. So we are assigning node voltages. Here node, when you assign node voltage here, for all nodes there should be some common point. That is what is the reference node or common node. Okay, so here we are applying voltage V1, that node plus and reference minus. Here this is node 2, voltage V2. At node it is plus, at reference it is minus. So we have to assign node voltages with respect to the reference node. Okay, at node it is plus, at reference it is minus. Likewise, we have to assign node voltages to all nodes. Okay. Now, next by using KCL, and Ohm's law. What is KCL states? The sum of currents entering is equal to the sum of currents leaving from the node. Okay. So, according to KCL, there first we have to write currents. Then by using Ohm's law and by using node voltage, we have to express those currents in terms of node voltages. Okay, first we write at this node 1 we write KCL, at this node 2 we write KCL. So whenever you write KCL, that in terms of the currents. Okay, so after getting that, by using Ohm's law, we have to express those currents in terms of node voltages. So if you see here, apply KCL and tell me at node 1. Apply KCL and tell me at node 1.
I of t is
Entering,
entering, sir.
Minus I.
V by,
Okay, no need to write, Why? Because the current source, nothing but that is current directly, it is available. Okay, whenever there is some current source, no need to express that current in terms of voltage. Why? Because directly we are having current constant. Okay, that's why no need to express in terms of voltages. Okay, students, one more point to say, that is at any node, our assumption is the current is leaving from that node. At any node, the assumption is all currents from that node are living currents. Okay, if I am considering this node, the current is living. So the assumption is living current. That's why since this is entering, that is minus I of t. Okay, that is minus I of t plus what is this? What is the current flowing to this branch? That is, let's say IR1. Okay, IR1 is equal to V1 minus 0 divided by R1. That's okay.
Okay, sir.
So now tell me, from here it is living current. So what is the current flowing through capacitor formula?
I equal to C into dV by dt.
Yes or no? So that is C into d by dt of V1 minus V2. Is it okay?
Okay, sir.
So now at this node, the equation is minus I of t plus V1 minus 0 by R1 plus C into d by dt of V1 minus
V1
V2.
minus V2.
That is equal to 0. Yes or no? Is it okay?
Yes, sir.
Okay, that's about KCL, nodal equation corresponding to node 1. Second node apply KCL again. Tell me. Hmm.
IL,
IL,
IR2,
IR2,
C into dV2 minus V1 by dt.
C, that is C into D V2 minus V1 corresponding to, I told you, corresponding to this node. So that is IC is equal to C into D by dt of V2 minus V1 plus, what is IL is equal to formula? Current flowing to inductor, IL is equal to
1 by L into
integral
V dt.
V2 minus 0 by dt, that is V2 dt.
Yes,
Now
sir.
tell me for this branch, what is the current? So the current is living like this, that is V2, current is plus to minus, that is V2 minus V minus 0 divided by R2 plus R3. Yes or no?
Yes, sir.
The current corresponding to this branch, that is V2 in the direction of current plus minus. That's why V2 minus
Minus
V of
V.
t minus 0. At this point, 0 reference, what is the voltage? 0 or not?
Yes, sir.
Okay, that's why V2 minus V divided by R2 plus
R2 plus
R3,
R3.
because these two are in series. Is that okay? Now tell me whole KCL equation here. That is C into d by dt of V2 minus V1
Minus V1.
plus 1 by L into integral
Integral
V2 dt
V2 dt.
plus
I2.
uh,
I,
V2
V2 minus V divided by R2 plus R3.
is equal to 0. Those two are the equations, node equations corresponding to the this circuit. Okay, so I mean that is what is written here, nothing new. Okay, at node 2 KCL. So the first equation is at node 1 KCL, second equation at node 2 KCL. That is what we told you already. C into d by dt of V2 minus V1 plus 1 by L into integral V2 dt plus V of t by, V2 minus V of t by R2 plus R2 is equal to 0 by using Ohm's law. Okay, so nodal analysis is nothing but KCL plus Ohm's law. When you write KCL, you will get expression in terms of current. When to express those currents in terms of node voltages, we have to use Ohm's law. That's why KCL plus Ohm's law gives you the nodal equation. Shall I proceed?
Yes, sir.
Similarly, mesh analysis. Mesh is corresponding to the loop or closed circuit. Okay. So now, students, to apply mesh analysis, first of all, we have to identify number of loops present in the given circuit. Okay. Here, in nodal analysis, our requirement is to find the node voltages. In mesh analysis, our requirement is to find the mesh currents or loop currents. Okay, if you know already loop current, so after identifying number of loops, we have to assign currents in clockwise direction. Okay, in mesh analysis, step number 1 is identifying the number of loops. Step number 2 is we have to assign currents to each loop in clockwise direction. So here, this first loop, when you assign current clockwise, there is a current source in the outer edges of the loops. Okay, here we are having the current in the outer edge of the loop. Okay, that's why this loop current is nothing but the value of this current source. Okay, if the loop current direction matches with the source current direction, then there is plus. Otherwise, if this loop current direction is opposite to that of this, current source direction, then the value will be minus. Okay. So whenever after we have to identify number of loops. After identifying number of loops, second step is we have to observe, is there any current source in the outer edges of the loops. If it is there, then that loop current is equal to the value of that current source. When the loop current direction matches with the current source direction, then it is plus. If the loop current does not match with opposite to the current source direction, then it is minus. Okay. So for that loop, no need to apply KVL. Why? Because our requirement is loop current. Already we got loop current from the given information. So once you know loop current, no need to apply KVL to that loop. Similarly, for nodal analysis also, once you know node voltage, then no need to apply KCL to that node. Right? Because there our requirement is node voltage. Here our requirement is loop current or mesh current. Okay. That's why I didn't prefer to assign current to this loop. Why? Because already directly you know the current of the loop current or mesh current. Still you can assign I1, where I1 is equal to I of t. Because the current we have to assign in clockwise direction. When you assign current in clockwise direction, that is matching with the current source. So that's why, let's say if you assign I1, I1 is equal to I of t. So once you know loop current, no need to apply KVL. For remaining two loops, we have to apply KVL. So before applying KVL, already I told you, in the direction of current or passive elements, we have to assign plus minus polarity. That is what is the I did here. Okay. For passive elements, in the before applying KVL, for passive elements in the direction of current, we have to assign plus minus polarity. Okay, that is what we are doing here. So plus minus here, plus minus, plus minus. Once you are done with that, then apply KVL to that loop. Okay, apply KVL. When you apply KVL, tell me. Plus to minus. Students, please respond.
For I2 current, sir.
For this loop, I am asking KVL equation.
Minus VL.
Minus VL, very good.
Minus VR2.
Okay.
Minus V of t.
Okay.
Minus VR3 equal to 0.
Equal to 0. So that is KVL gives you the algebraic sum of voltages inside a loop is equal to 0. Now we have to express those voltages. So students, please remember here, if there is some suppose you are having voltage source like this, for this no need to use KCL, Ohm's law. Why? Because already you know voltage, directly you can just express it. But remaining elements, we have to express those voltages in terms of the loop currents. Okay, tell me what is VR2 is equal to? What is the current? What is this loop current?
I2 into R2.
R2. What about VR3 is equal to?
I2 R3.
I2 R3. Very good. What about VL is equal to?
L into di2 minus di1. D by dt into I2 minus I1.
Very good. Very good. Very good. Very good. Why? Because the current flowing through this element L is corresponding to this loop, that is I2 minus I1, corresponding to this loop, that is I1 minus I2. Okay, if we apply KVL in this loop, then we have to use L into d by dt of I1 minus I2 corresponding to this loop. Corresponding to this loop, L into d by dt of I2 minus I1. Okay, now tell me once again the KVL using loop currents.
Sir,
I need in terms of currents.
I2 R2.
Plus or minus? KVL.
Minus I2 R2.
Okay, very good.
Minus V of t.
Okay.
Minus I2 R3.
Okay, very good.
Minus of L L into d by dt of I2 minus I1.
Very good, very good. Thank you. That is what is here. Nothing new. Okay. So whenever there is some common element between two loops, now tell me KVL for this loop. Tell me, I mean yourself.
I1 R1.
Don't do mistake. R1 is common to these two loops. Tell me.
R1 into I1 minus I of t
Whether that is plus or minus before sign.
minus
Tell me again. Minus.
R1 into I1 minus I of t
Okay.
minus
Minus one.
C into
No. 1 by C into.
1 by C into I1 integral I1 dt.
Okay, very good.
L
Minus.
minus L into d of I1 d by dt of I1 minus I2 equal to 0.
Very good. Very good. So before applying KVL in mesh analysis, we have to assign plus minus polarity in the direction of current to all passive elements. Okay, that is the point to be noted. So that's about brief about mesh and nodal analysis. So along with that, we may have some special cases. Whenever there is only voltage source between two nodes, then we have whenever there is only voltage source between two nodes, okay, then we have to go for super node analysis. Okay, whenever there is a common current source between two loops, whenever there is common current source between two loops, then we have to go for the super mesh analysis. Okay, whenever there is only voltage source between two nodes, then we have to use super node analysis. So I will explain later what is super node and super mesh analysis. Okay.
Okay, sir.
Shall I proceed?
Yes, sir.
Okay, and then next part is the equivalent circuits. I mean, already we know. Series, whenever the elements are connected in series, the current flowing through those elements is same. Whenever the elements are connected in parallel, the voltage across all elements is same. Okay, that is why the voltage across parallel elements is same. The current flowing through series elements is same. Simply, I wrote here directly for the impedance case also. Okay, so what is when these two are connected in series? Tell me what is the equivalent impedance?
Z1 plus Z2.
Okay, so Z can be Z1, Z2. That Z may be the impedance, may be pure resistance, or it may be pure reactance also. Okay, when you express impedance in terms of pure resistance, that is Z1 is equal to R1 and Z2 is equal to R2. Tell me what is the equivalent resistance?
R1 plus R2.
Yes. Suppose in terms of inductance, that is reactance, that is j omega L1, j omega L2. What is the equivalent inductance?
L1 plus L2.
If it is capacitance, tell me first, what is the capacitive reactance? 1 by omega C. Yes or no?
Yes, sir.
Like inductive reactance is omega L. That is, you can say in terms of impedance, that is j omega L. For the capacitor, the impedance is j by omega. I mean, that is 1 by j omega C, or you can say minus j by omega C. Okay. For resistance, the impedance is Z is equal to R. For the inductance, the impedance Z is equal to j omega L. For capacitance, Z is equal to 1 by j omega C. Now tell me, don't look at this slide or screen. Tell me, if these two are resistors, Z1 is equal to R1, Z2 is equal to R2, what is the equivalent resistance?
R1 plus R2, sir.
If these two are inductances,
L1 plus L2.
capacitors,
1 by C1 plus 1 by C2.
so that is left side is 1 by C equivalent is equal to 1 by C1
1 by
plus
C1 plus 1 by C2.
Thank you. Now similarly, we can also connect these elements in parallel. Tell me, when these two are connected in parallel, what about equivalent resistance?
One R1 R2 by R1 plus R2, sir.
So that is R equivalent is equal to R1 R2 by R1 plus R2. Or you can say 1 by R equivalent is equal to 1 by R1 plus 1 by R2. What about in the equivalent inductance?
1 by L1, 1 by L equivalent equal to 1 by L1 plus 1 by L2, sir.
So what about capacitance?
C equivalent is equal to C1 plus C2.
Very good, very good. Okay, now now we'll come to voltage division principle. What is voltage division principle? Tell me. Suppose the total voltage source, the total voltage connected across n number of series elements. Total voltage connected across n number of series elements. Suppose I need voltage across particular element. So there we have to use this voltage division principle. Okay. So now students, if you see here on this network, what is the total current? Tell me. This is the applied voltage V. What is the total current? I is equal to V by Z equivalent or not?
Yes, sir.
So what is Z equivalent?
Z1 plus Z2.
Z2. So the total voltage V is equal to I into Z equivalent, or I is equal to V by Z equivalent, where Z equivalent is equal to Z1 plus Z2. Now tell me, what is the voltage across Z1 using Ohm's law? V is equal to V1 is equal to
I into Z1.
where what about I is equal to V by
Z1, sir.
V by
Z1.
no, I am asking I total current I is equal to. So see,
V by Z1 plus Z2, sir.
if you want to say in terms of Z1 that I is equal to V1 by Z1, you can say. Now my question is, you know V1 is equal to I into Z1. What is total current I is equal to?
V by Z1 plus Z2, sir.
Z2, that is V by Z equivalent. Z equivalent is equal to Z1 plus Z2. Now tell me, what is V1 is equal to in terms of V?
V1 equal to V into Z1 by Z1 plus Z2.
Very good, very good. Similarly, tell me, what is V2 is equal to?
V by VZ2 by Z1 plus Z2, sir.
So the total voltage connected across n number of series elements, the voltage across particular element, let us say Z1, that is equal to total voltage into corresponding impedance divided by sum of the impedances. Okay, so that is what is V1 is equal to V into corresponding impedance is Z1 divided by sum of these two, that is Z1 plus Z2. Similarly, V2 is equal to total voltage V into corresponding impedance Z2 divided by Z1 plus Z2. So that is what is voltage division principle. Okay. So for resistor, it is corresponding resistor. I mean V1 is equal to V into R. I mean when Z is equal to R, V1 is equal to V into R1 by R1 plus R2. For the inductor also same, that is V into L1 divided by L1 plus L2. The voltage across R1, that is V1 is equal to V into total voltage V into corresponding resistance by sum of the resistances. Similarly, V2 is equal to total voltage into corresponding resistance by sum of the resistances. Similarly, for inductance also, that is total voltage into corresponding inductance divided by sum of the inductances. Similarly, total voltage into corresponding inductance divided by sum of the inductances. But when it comes to capacitor, the relation is different. That is total voltage, I mean the voltage across capacitor V1 is equal to total voltage into opposite capacitance. Suppose we are having two capacitances. What is the opposite capacitance? C2, yes or no?
Yes, sir.
So that's why for capacitor the relation changes. For inductor and resistor the relation is same, that is V into R1 or V into L1 by R1 plus R2 or L1 plus L2. But when it comes to capacitor or capacitance, V1 is equal to total voltage V into opposite capacitance C2 divided by C1 plus C2. Similarly, V2 is equal to total voltage into opposite capacitance, the other capacitance C1 divided by C1 plus C2. So this V1 and V2 So whenever to find voltage across V1 V2 like this, we have to have only two capacitors in series. Okay, more than two means we have to look after. Okay, now next we will see parallel connection. Okay, so in parallel voltage is same or current is same? Tell me.
Voltage same.
Voltage across elements is same. So now, so what is the, by using Ohm's law, tell me what is I1 is equal to in terms of V?
V by Z1.
I2 is equal to?
V by Z2, sir.
Now apply KCL at this point. Tell me. KCL at this node or at this junction. Students, KCL at this node or at this junction. Tell me, apply KCL. What happened? Please respond. So when you apply KCL at this point or at this junction or at this node, this is the entering current minus I. These two are leaving currents. That's why I is minus I plus I1 plus I2 is equal to 0. I is equal to I1 plus I2. So, okay. Now, students here, whenever the impedances are connected like this, the total admittance is equal to sum of the admittances. So, impedances in series can be added directly. The admittances in parallel can be added directly. Now, admittance Y is equal to Y1 plus Y2. So what is Y equivalent is equal to 1 by Z equivalent. What is Y1 is equal to 1 by Z1. What is Y2 is equal to 1 by Z2. Is my voice audible? Can you hear me?
Yes, sir.
Okay, thank you. So now, so impedances in series can be added, whereas admittances in parallel can be added simply. So in that way, Y equivalent total admittance Y equivalent is equal to Y1 plus Y2. So Y equivalent is nothing but 1 by Z equivalent. Y1 is nothing but 1 by Z1. Y2 is nothing but 1 by Z2. So this comes like this: 1 by Z equivalent is equal to 1 by Z1 plus 1 by Z2. When these two impedances are resistances, tell me what is the equivalent resistance?
R1 R2 by R equivalent is equal to R1 R2 by R1 plus R2.
Okay, general formula is 1 by R equivalent is equal to 1 by R1 plus 1 by R2. Suppose now tell me when these two are inductances.
1 by L equivalent is equal to 1 by L1 plus 1 by L2, sir.
Suppose these two are capacitors.
C equivalent is equal to C1 plus C2, sir.
Okay. Now for this, here since current is dividing, we can use current division principle. In series, current flow is same, but voltage gets divided. In parallel, voltage across elements is same, but current gets divided. Okay. So to find the currents I1 and I2, we can use current division principle. Now tell me what is the equivalent admittance, equivalent impedance of this circuit?
Z1 Z2 by Z1 plus Z2.
Now tell me what is V is equal to?
I into Z equivalent.
Okay, I into Z equivalent. Now what is the I1 is equal to V by
Z1, sir.
What about V is equal to I into Z1 Z2 by Z1
plus Z2.
So you know I1 is equal to V by Z1. Okay, you also know V is equal to I into Z equivalent, that is I into Z1 Z2 by Z1 plus Z2. Substitute here. I1 is equal to V by Z1, where the V is equal to I into Z1 Z2 by Z1 plus Z2. So when you substitute here, what happens?
Z1 will
gets cancelled out. I1 is equal to I into Z2 by Z1 plus Z2. Similarly for I2. Now, so to find current, this I1, that is current flow, total current, okay, in parallel with two branches. Okay, total current in parallel with the two impedances. The current flowing to first impedance I1 is equal to total current I into what is the opposite impedance? Z2 divided by Z1 plus Z2. Okay, the current flowing through impedance Z1 is equal to I1 is equal to total current I into opposite impedance Z2 divided by Z1 plus Z2. Similarly, the current flowing through Z2, that is I2, is equal to I into total current I into opposite impedance Z1 divided by Z1 plus Z2. Okay, so students, whenever you apply current division principle, what you have to do is, whenever you suppose you want to apply this formula directly, at that time what you have to do is, you have to make sure that there is some total current that is in parallel with the two impedances or two resistances or two inductances or two capacitances. Okay, then you can directly apply this current division principle. The current flowing through Z1 is total current I into opposite impedance by Z1 plus Z2. Current flowing through I2 is equal to I into Z1 by Z1 plus Z2. This is what is current division principle. So here I wrote for the resistor, inductor and capacitor. For resistor it is I into R2 by R1 plus R2. For inductor also I into L2 by L1 plus L2. But when it comes to capacitor, total current into corresponding capacitance. Okay, na? In voltage division principle, for inductor and resistor, total voltage into corresponding resistance. When it comes to current division, total current into corresponding capacitance. There it is in voltage division principle, total voltage into opposite capacitance. Here for capacitor, for the resistor and inductor, total current into opposite resistance. Is that okay, all of you?
Yes, sir.
Shall I proceed?
Yes, sir.
Okay, thank you. Next, you will see when you are reducing network like resistances, inductances, capacitances, at in some situations, you cannot use series connection or parallel connection. There may be chance for star to delta conversion or delta to star conversion makes your network, or you can reduce your network by using these two techniques. When there is no scope for series connection or parallel connection, at those instances, at those times, you can use this star to delta, the delta to star network to reduce the given network or given circuit. Okay, students, this is delta, Z1, Z2, Z3, and star is ZA, ZB, ZC. So here what I am giving, delta is given, I am asking for star. Here delta to star, delta is given, I am asking for star. So the impedances corresponding to delta are Z1, Z2 and Z3. Now I am asking for ZA, ZB and ZC. Okay, now, so I am asking ZA. For ZA, what are the adjacent elements? Z2 and Z1 and Z3. So ZA is equal to the multiplication of adjacent impedances divided by sum of all impedances. That is, ZA is equal to Z1, ZA is equal to Z1, Z3 divided by Z1 plus Z2 plus Z3. So here delta network is given. That is what is Z1, Z2, Z3 is given. I am asking for star network values. That is ZA, ZB, ZC I am asking. ZA is equal to Z1, Z3 divided by Z1 plus Z2 plus Z3. Okay. Now tell me, what about ZB is equal to? Any of you? Please tell me what is ZB is equal to. Please respond here. Don't sleep.
Z1, Z2 by Z1 plus Z2 plus Z3.
Very good. What about ZC is equal to?
Z1, Z2, Z3 by Z1 plus Z2 plus Z3.
Okay, very good. So that's for delta to star conversion. Suppose if I am giving star network, that is ZA, ZB and ZC are given, I am asking for Z1, Z2 and Z3. To find, suppose I need Z1. What you do is, first multiply these three in cyclic manner. That is ZA, ZB plus ZB, ZC plus ZC, 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 ZA. ZA, ZB plus ZB ZC plus ZC ZA whole divided by what is the impedance? I mean opposite to this Z1. For Z1, the exact opposite is ZC. So ZA ZB plus ZB ZC plus ZC ZA whole divided by the impedance which is opposite to this Z1, that is ZC. That's why ZA ZB plus ZB ZC plus ZA ZB by ZC. Or simply you can write ZA plus ZB plus ZA ZB by opposite ZC. Okay, I mean whichever way, that is both are fine only. AB, BC, CA. Okay, divided by opposite is ZC. ZA ZB plus ZB ZC plus ZC ZC. ZC ZA whole divided by ZC. That gives you ZA plus ZB plus ZA ZB by ZC. Now tell me similarly, what about Z2 is equal to?
ZP plus ZC plus ZB ZC divided by
ZA opposite.
ZA.
Similarly, Z3 tell me.
ZC plus ZA plus ZA into ZC divided by ZB.
So exact. See, students, don't think like sir. I mean, it should look like star or delta. Okay, whenever, I mean, sometimes it may be T network, it may be delta network, like that also. So you have to make that delta into star, delta into, I mean, sometimes they'll give pi network. Pi is nothing but delta. Sometimes they give T network. T is nothing but star network. Okay, so you have to be careful. Okay, so from delta to star, multiply adjacent elements and divide with sum of these three impedances. For star to delta, multiply cyclically AB, BC, CA and divide with opposite. Okay, we need Z1. What is the exactly opposite to that? ZC. AB, BC, CA divided by ZC. Okay, so that is how we have to convert from delta to star or star to delta. So students, suppose here ZA, ZB, ZC all are equal. ZA, ZB, ZC are all are equal. Tell me what happens to Z1, Z2, Z3. So let's say ZA is equal to ZB is equal to ZC is equal to Z. Okay, what happens to Z1?
3Z.
3Z, yes. Okay, so means suppose if the given network is star network, okay, or else you can say like that. In a given star network, if all the impedances are equal or same, then the impedances present in corresponding delta network becomes are increased by 3 times.
3 times.
3 times, yes, simply to say. So suppose the given star network consists of 3 impedances, all are equal. Okay, the impedance that becomes multiplied by 3 times when you convert from star to delta. Okay, the star network with same impedances or same resistances, when you convert into delta network, the resistance is increased by 3 times. Okay, that is what is given here. So by delta transformation, that is star to delta network transformation, will increase the impedance by 3 times. Similarly, delta Y transformation, what happens? That is delta to star. Suppose Z1, Z2, Z3 all are same. What about ZA is equal to? So let's say Z1 is equal to Z2 is equal to Z3 is equal to Z. What is ZA is equal to?
1/3 into Z.
So whenever the given delta network consists of all equal impedances, that is Z, then when you convert it into star network, the impedance is reduced by 3 times. Yes or no? No. So from delta to star, the impedance delta network, star network with all equal impedances, when you convert it into delta network, the impedance is increased by 3 times. Okay, so the other way is the delta network with all equal impedances, when you convert it into star network, the impedance is reduced by 3 times. Yes or no?
Yes, sir.
Okay, thank you. So the equivalent circuit with respect to the sources point of view, I mean, so these two are equivalent, right? Because the current flow, since these two are connected in series, the current flowing through this is whenever R1 is not equal to infinity here. Okay, so I mean, see, so the resistor in series with ideal current source that can be neglected in analysis of the sorry. So suppose if I am finding load resistance here, I am applying current I am finding out load current. So whenever you are finding some load current, that will be equal to the source current. Why? Because here the resistor is connected in series with the current source. Okay. So whenever you are measuring load current for this kind of network, you can ignore this resistor. Okay. Why? Because the current flowing through this resistor is same. Why? Because this resistor is connected in series with the current source. Okay. Whenever you are measuring load current, you can ignore this resistor. Why? Because the current flowing through this resistor is same. Similarly, whenever you are connected resistor in parallel with the voltage source, whenever you are measuring load voltage, you can ignore this resistor. Why? Because parallel, the voltage is same. The voltage across R1 is equal to V. That is nothing but the load voltage here. Okay. Whenever you are measuring load current here, you can ignore this resistor. Why? Because this is connected in series with this current source. The current flowing through this resistor is same as I. That's why you can ignore this resistor. Similarly, whenever you are connected this voltage source in parallel with the R1, whenever you are measuring this load voltage, that will be equal to V. You can ignore this R1. Why? Because the voltage across R1 is V. Okay. Now please look at here. So is this valid? Please look at the screen and tell me, is this valid?
No, sir.
Why? Why this is not valid? So current sources connected in series.
Series.
Current sources are connected in series. The value of those current sources must be same.
Same.
Otherwise, it is violation of KCL. Okay, so that's why it is invalid. Now, what is the valid condition? I is equal to I1 is equal to I2. Whenever current sources are connected in series, the value of those current sources must be same. Otherwise, the violation of KCL. Okay. Now tell me, what about these two? What is the condition to be satisfied? Okay, here V1 is equal to V2. Whenever we are connecting voltage sources in parallel, the value of those voltage sources must be same. Okay. So student, if you change the minus to plus, this should be minus V2. Means if this is plus 5, plus minus with 5 volts. Here you have to have plus minus with 5 volts or minus plus with minus 5 volts. Same or not? See, suppose I am giving voltage source plus minus with 5 volts, that is equivalent to the minus plus with minus 5 volts. Yes or no?
Yes, sir.
Okay. So here, I mean, these two voltages must be same. Otherwise, violation of KVL. So that is what is written here. Whenever two ideal current sources are connected in series, their magnitudes must be same. Okay, the two current sources are more than two current sources whenever they are connected in series. The values of the magnitudes of those current sources must be same. Okay. Similarly, for parallel connection, voltage must be same. Now, students, please look at here. Tell me Suppose if I am connecting two voltage sources in series, I mean, is there any necessity that V1 is equal to V2? Is there any necessity?
No, sir.
No, there is no necessity that V1 must be equal to V2. Why? Because we can connect any number of voltage sources in series with different values and different polarities. Okay, that is your choice. Okay, now apply KVL and tell me what is V is equal to. Tell me KVL.
V1 plus V2.
V is equal to V1 plus V2. Suppose if I am giving minus plus here, tell me.
V1,
Here.
V2 minus V1.
Very good, very good. Suppose if I am putting minus plus here minus, here plus, what is equivalent?
Minus V is equal to V1 plus V2.
Or you can say V is equal to minus V1 plus minus V1 minus V2. Means, so if you change minus plus here, this becomes minus V1 minus V2. If it is plus minus, that is V1 plus V2. I mean, that is, that depends on how, how you are considering your polarity. Okay, now tell me, so is there any necessity that I1 is equal to I2? Whenever current sources are connected in parallel, is there any necessity that I1 must be equal to I2 like that? Please respond. Please. So, whenever two current sources are connected like this parallel, okay, is there any necessity that I1 must be equal to I2?
No, sir.
No, there is no necessity. So you can connect n number of current sources in parallel. Okay, whatever may be the direction of current, it may be upward direction, it may be downward direction. You can combine all those current sources and you can replace with single current source. Okay, the current, so you can connect n number of current sources in parallel. Moreover, you can replace all those current sources by using single current source. Okay, the value of that single current source depends on the current sources which you are connected in the parallel. Okay. Now, if you combine, apply KCL, tell me, apply KCL at this node, tell me what is I is equal to. Apply KCL at this point and tell me what is I is equal to.
I1 plus I2.
So, minus I1 plus minus I2 is equal to minus I1 minus I2 plus I is equal to 0, I is equal to. Suppose when you put downward direction here, what is this I is equal to?
Minus I1 minus I2.
Minus I1 minus I2, very good. Okay, so similarly you can see this kind of circuits. Now question, determine the current flowing through the 5 ohms resistor. I am asking you to find the current flowing through the 5 ohms resistor. Tell me what is the current flowing through this 5 ohms resistor. This is circuit given. I am asking you to find the what is the current flowing through this 5 ohms resistor. Can you hear me?
Yes, sir.
Tell me. What is the current flowing through this 5 ohms resistor? So students, if you observe here, so this here two voltage sources, all these three branches, they are connected in parallel, yes or no?
Yes, sir.
Okay, so in these three parallel branches, we are having two voltage sources. What is the value of this voltage source?
5 volts.
What is the value of this voltage source?
10 volts.
So whenever two voltage sources are connected in parallel, what is the condition to be satisfied? In parallel, what is same, whether current or voltage?
Volt.
Huh? Tell me completely.
Voltage, sir.
Voltage same, but what happens here? So here two voltage sources are connected in parallel, but
But they are not
the
same.
voltages are not equal. So here it is 5 volts, here it is 10 volts. Violation of KVL. You can't find the current flowing to the 5 ohms resistor. Violation of KVL. Okay, so that's why since the circuit is violating KVL, we cannot determine the current flowing to the 5 ohms resistor. Okay, is that okay? Please tell
Yes,
me.
sir. Yes, sir.
Now tell me what about this? Same question. The current flowing to 5 ohms resistor.
Same.
Why? 10 volts only, na?
Yes, sir.
And then
Polarities are
very good,
different.
very good. So here it is plus minus
Plus
10
10,
volts. Here it is plus minus 10 volts.
minus 10 volts.
So the voltages are not same. So that is what is violation of KVL. That's why you can't determine. Next, this one tell me.
10.
So what is the current flowing to 5 ohms? Yes, it is 2 amperes or not.
Yes, sir.
Even though two voltage sources are here and the value of those two voltage source
Are same.
same. Okay, here it is 10 volts, here also it is 10 volts. Okay, there is no violation of KVL. So you can find the current flowing to this resistor 5 ohms. That is by using Ohm's law. I is equal to V by R. What is V? 10 volts.
10 volts.
Is 5
10
ohms.
by
10 by 5, that is
2 amps.
Is this okay? Is
Yes,
it
sir.
clear about process? When they are connected in parallel, when they are connected in series, what are the conditions to be satisfied? Okay, shall I proceed?
Yes, sir.
Next. Now tell me, what is the voltage across 2 ohms? What is the voltage across 2 ohms resistor? Please tell me.
Uh,
What is the problem
three,
with this circuit?
నాట్ అక్కడ అవి రెండు సేమ్ కాకుండా వేరే వేరే డైరెక్షన్ లో వెళ్తున్నాయి.
Okay, two current sources are given in series, but their
they are
magnitude
not
are not same. Okay, this is the upward, this is downward. Okay, that's why violation of KCL. At this point, when you apply KCL, it has to satisfy. Okay, but it is not satisfying. At this point, when you apply KCL, this is living plus 3, this is also living plus 2, 2 plus 3 is equal to 0. It is not valid. Okay, 5 is equal to 0. The 5 never be equal to 0 in KCL. At some point, when you apply KCL, it has to satisfy sum of entering currents is equal to sum of living currents. Okay, violation of KCL, you can't determine the value they are asking for. That is V naught. Okay, what is Telegrams theorem states? Tell me. I told you already, each and every network or each and every circuit, they must satisfy the Telegrams theorem. Tell me, what is that Telegrams theorem states that?
Power must be same.
Don't say, I mean, that's okay, but total power delivered is equal to total
power observed
in a given circuit or in a given network. Okay, so whatever the amount of power delivered in the circuit, that amount must be observed. Otherwise, that is invalid network. Okay, whatever the power delivered in the given network must be observed. Otherwise, that is not a balanced thing. Okay, So each and every network or each and every circuit, they must satisfy elegance theorem. Okay, total power delivered in a network is equal to total power absorbed, or you can say total power delivered in a network is equal to zero. Okay, na? If it is power deliver, so total power delivered in a network is equal to zero. So what it means is, for all elements you have to find the power delivered. Okay, so in terms of quantity, I mean the value. So for some elements, power delivered is positive. For other elements, power delivered is negative. When you combine these two, that will be equal to zero. Okay, na? Total power delivered in a given network is equal to zero. Means for all elements given in the circuit or network, you have to find power or you have to perform power calculation. Then after getting all those powers, add them. That will be equal to zero. So that is what is total power delivered in a network is equal to zero. Okay. Next
Okay,
one
sir.
is total power absorbed in the network is equal to zero. What it means is for all elements given in the network or circuit, you have to find the power, add them. That will be equal to zero. Right? How means the power absorbed is positive for some elements, negative for some elements. If you combine all those things, that will be equal to zero. That is what is, or else total power delivered is equal to total power absorbed. All these three statements, they gives same information only. Okay, total power delivered is equal to total power absorbed, or total power delivered in the network is equal to zero, or total power absorbed in the network is equal to zero. Students, please observe, power absorbed or power consumed or power dissipated. These three are same only. Don't confuse. Okay, power absorbed or power consumed or power dissipated. Okay, so resistor dissipates power in terms of heat. Whenever you are conducting some or you are conducting some experiment, resistor absorbs power, or you can say resistor dissipates power. So dissipates means in terms of heat, it is losing some power. That is what is we are saying power dissipated. Okay, so power dissipated by the resistor, or power absorbed by the resistor, or power consumed by the resistor, or real power in terms of AC circuits, real power. All these are active power. Okay, power consumed by the resistor, power absorbed by the resistor, power dissipated by the resistor for DC circuits. Along with these three, for the AC circuits, they use real power or active power. All these terms belongs to the resistor. Okay, all these are same only. Okay, for DC circuits, it is V into I. For AC circuits, it is VI cos theta or VI cos phi. Okay, power dissipated, power consumed, power absorbed, all are same. Shall I proceed?
Yes, sir.
Okay, thank you. So now I am asking you to find the power related to the elements given in the network. Okay, now what we have to do first, whenever I am asking you to find the perform the power calculation, first of all you should know voltage across all elements and current flowing through all elements. Once you know voltage across all elements and current flowing through all elements, you just perform V into I, that gives you the power. Yes or no?
Yes, sir.
So that's why first find out the total current, that is voltage. Apply KVL, tell me what is the total current? Assign current I.
20
uh, minus 5 into I.
minus 5 into I plus minus 5 also equal to 0.
From this you will get I. Once you get I, now just listen to me. Whenever current is moving from minus to plus, the power delivered is equal to positive. Whenever current is from minus to plus, power delivered is positive, power absorbed is negative. Whenever the current direction is from minus to plus polarity, power delivered is equal to positive value. Power absorbed is negative. Similarly, whenever the current is from plus to minus, power absorbed is positive, power delivered is negative. Is it okay? Now tell me, you yourself tell me. Minus to plus. What about delivered?
Positive, sir.
Observed?
Negative, sir.
Plus to minus? Observed?
De- Observed positive, sir.
Delivered?
Negative.
Negative. Now if you see here, please don't confuse. Here it is minus to plus. The voltage is 20, current is 3. 20 into 3 is 60.
60 volts.
That is, since it is minus to plus, that is power delivered, that is plus. Or you can say here, student, put here observed, then what you have to do? You have to put here
Minus.
minus. Well and good. That satisfies our condition. Okay, I mean Telegrams theorem statement. Minus to plus, power delivered is positive. That is the value is V into I. V is 20, I is 3, 60 watts. Now here, similarly, plus to minus, power absorbed is positive. Or you can say you can put delivered here. Then what you have to do here?
Minus.
Minus. Plus to minus, absorbed is positive. That is the voltage is 15. How you get 15? By using Ohm's law. V is equal to I into R. I is 3 and R is 5. 5 into 3, 15. So the P 5 ohms is 15 into 3. That is observed. Now here also it is from plus to minus or not?
Yes, sir.
So that's why observed is positive 15. Now what is the total power delivered here? 60. Total power observed is
45 plus 15.
60. Yes or no?
Yes, sir.
Hence VTT verified. That is Telegrams theorem verified. Is that okay?
Okay, sir.
Okay, we'll see one more example. Now here I am asking for check or verify Telegrams theorem. So VTT means verify Telegrams theorem. Now here if you see current direction, this is the current direction, current 2 amperes. In this direction, so in the direction of current for passive element plus minus, that's okay. Is that okay?
Yes, sir.
Or else consider some node voltage V, put here plus, put here minus, apply KC. I mean, no need of that also. Even why? Because you are having voltage source in parallel. Yes or no? These
Yes,
two are
sir.
parallel or not. So now tell
Yes.
me what is the voltage across 2 ohms?
2 volts.
2 volts. So once you know voltage and resistance, you can find current. So
Yes,
here
sir.
it is plus minus, here also it is plus minus. So for passive elements in the direction of current, polarity is plus minus. Since polarity is plus minus here, current must be downward direction. Yes or no?
Yes, sir.
So here don't confuse. Here this is plus minus. So here this is parallel element. That's why the voltage is plus minus 2 volts only. So here the voltage is 2 volts and resistance is 2 ohms. Now we should know the direction of current. So for passive element in the direction of current, the polarity is plus minus. Since the polarity is plus minus here, the direction of current must be downward. Is my statement correct? No? Can you hear me?
Yes, sir.
So plus minus, that's why the current must be downward. So 2 volts divided by 2 ohms, that is equal to 1 ampere. Okay. So here the current entering is 2 amperes. Current leaving here it is 1 ampere. What about the current flowing in this branch? Apply KCL. See students here the current entering is 2 amperes. Here this branch current from this voltage source it is 1 ampere. So out of this 2 amperes, 1 ampere flows here. What about the current flowing in this branch?
1 amps.
1 ampere total current. Apply KCL and check whether it is satisfying or not. Yes. So entering is minus 2 plus 1 plus 1.
Plus
Minus
1.
2 plus 3 is equal to 0. Yes. KCL it is satisfying. Now after getting all those values, now tell me what is the voltage across. Now we need voltage across these 2 amperes. So students, for generally for current source, at arrow side plus polarity, at tail side minus polarity. Is that okay?
Okay, sir.
Okay, arrow side plus tail side, head is plus, tail is minus. So likewise consider polarity and apply KVL. Tell me what is V2A is equal to KVL. Minus 2 plus.
Plus
Tell me, apply KVL. Tell me the equation.
minus 4 minus 2.
Means
I mean,
V2A is equal to 6 volts.
yes, sir.
Now use power formula. P2A, that is power of a 2 ampere source, that is equal to V2A into 2. V2A how much? 6 into 2, that is 12 watts. Current direction is from minus to plus. That's why this is power delivered is positive. Here it is plus to minus 4 into 2, 8. That is plus to minus means power absorbed is positive 8 watts. This is plus to minus. Voltage is 2, current is 1. 2 into 1 plus to minus, that is absorbed is positive. Similarly here the current direction is plus to minus, that is 2 into 1, 2 watts absorbed is positive.
Positive.
Now tell me what is the total power delivered? 12 watts. What is the total power absorbed? 8 plus 2
2
plus
plus 2.
12. 12 is
12.
equal to 12. Is that okay?
Yes, sir.
Total power delivered is equal to
Total power absorbed.
Hence Millikan's theorem verified. So likewise you can solve any number of problems. So here also this is one more example corresponding to the. Shall I explain or I mean you can do it on your own?
Sir, we will try to do, sir.
Okay, very good, very good. That's the spirit. So I mean, so the thing, see, you know all basics. You know KVL, you know KCL, you know Ohm's law, you know nodal, you know mesh. So I mean, whichever technique you, I mean, that is your choice, your wish. There is no necessity that you have to use KVL. There is no necessity that you have to use KCL. Whichever method gives you answer in less time, that method you have to use. That comes from practice. Okay, I mean that will never come overnight. So means you may ask question like this, which method is best suitable? That comes from practice. I can't decide. I can't tell even, you know. That comes from practice. So when you practice more problems, you will get more experience and you will come to know the method, whichever method is suitable for that particular case or particular problem or particular circuit. Okay, that gives you answer in less time. That is what is important. Okay.
Okay, sir.
Now, so there is some glitch here problem. We'll see what is that problem here. So here, so I mean, if you see here, so I am giving this is current source downward 0.25. This is voltage source 3 volts. I am asking you to find what is the power absorbed or power delivered. So same thing like students here, the thing is the current flowing through voltage source. The current flowing through voltage source may be any value, or the voltage across current source may be any value. Okay, the current flowing through voltage source may be any value. The voltage across current source may be any value. Okay, so I mean for that try to do calculation. So here these two are in parallel. What is the voltage across this one? 3
3
volts.
volts.
So once you know voltage and resistance, you can find current. That is plus minus. That's why the current is downward current. This is 0.75 ohms. It is not ohms. It is amperes. Mistake.
Okay.
Amperes. Okay. So now, so you know, I mean, here the voltage across this current source also equal to 3 volts. The voltage across this current source also equal to 3 volts. Yes or no? Why? Because these three are connected in parallel. So once you know, so I mean here the current is 0.25 amperes. Here the current is 0.75 amperes. What is the current flowing through this branch by using KCL? Yes or no?
Yes, sir.
Means for passive elements, for the thing here is for passive elements, you can find voltage across or current flowing through that elements by using Ohm's law. But when it comes to voltage source or current source, for voltage source, you can't directly find current flowing through that voltage source by using Ohm's law. Yes or no? See,
Yes, sir.
3 volts here. You can't directly say what is the current flowing through this directly. Why? Because you don't know the internal relations of this. Okay, that's why it is the current flowing through this voltage source depends on the other elements in the circuit. Okay, so here if you see here, what happens here? This is 100 volts. This is 2 amperes. This is 3 ohms. So the voltage across this 2 amperes is 10. The voltage across this 3 ohms is also 10. So now here it is 10 by 3. 10 by 3 or not?
Five, sir, 5 ohms. Sir.
5, I'm sorry. 10 by 5 that gives you 2 amperes. So you can't directly find the current flowing to this 10 volts source. It may be any value. So to find the current flowing to this 10 volt source, we have to use KCL. We can't use Ohm's law. The thing is, we can't use Ohm's law.
Ohm's law.
So that is what is given here from the above two problems. The current flowing through the this is ideal voltage source. Why? Because nothing is connected in series at all. Nothing. This is voltage source. Nothing is connected in series. This is ideal voltage source. Yes or no?
Yes, sir.
Okay. So the current flowing through an ideal voltage source can be any value. It is decided by the other elements. That is what I told you now. So
Yes, sir.
the current flowing through this ideal voltage source is decided by the remaining elements present in that network. Okay.
Okay, sir.
Similarly, for the current source also you can give an example. Okay. So in this case, the current flowing through this ideal voltage source, you can't, you can't directly decide. That will be decided by the current flowing through remaining elements. Or you can say that is decided by the remaining elements present in that network or circuit. Is that okay?
Okay, sir.
Okay, thank you. So the voltage across ideal current source, same thing, other way. So the current flowing through So I'm sorry, there is a problem at my end. Students,
Yes, sir.
thank you. Sorry for disturbance. Sorry for disruption. Okay. So here, I mean, I told you already, source transformation is nothing but voltage source in series with the resistor can be transformed to current source in parallel with the same resistance. Okay. Here, in this network, you may feel like, sir, I can apply, I mean, source transformation here. Why? Because the voltage source in series with the resistor, but you cannot apply. Why you cannot apply? Tell me. Why you cannot apply source transformation here?
Sir, screen share అవ్వలేదు sir.
Oh, sorry. Now, is it visible?
Yes, sir.
Okay. Here, I mean, so you may feel like, sir, I can apply source transformation here. Why? Because voltage source in series with resistor, but you cannot. Why? What is the reason?
Dependent source.
Dependent variable. Okay.
Yes,
So
sir.
because of dependent variable present in this branch, you cannot apply source transformation technique. Okay. I told you already, note point last week itself. The branches with dependent variables, source transformation technique is not applicable. Okay. So next you can see here, you can observe. So here when so this voltage source in series with the resistance, that is 4 in series with 2. Now transform it into current source in parallel with the resistor. What happens to current source value? So the voltage source in series with the resistor. Now I'm asking you to transform this into current source in parallel with the same resistance. What is the value of that current source? I is equal to V by R.
V
Yes or
by
no?
R. 4 by 2
V is
2. Yes, sir.
what is the direction? That is from negative to positive. That
Negative
is
to
the
positive.
upward direction.
Words. Yes,
Okay.
sir.
Here it is 1 ampere in parallel with 2 amperes. Okay. You can combine current sources in parallel. 1 ampere
Yes,
upward
sir.
direction. Here also 2 amperes upward direction. 1 plus 2 becomes 5.
3 amps.
Okay. And one more thing, 2 ohms in parallel with 2
2
ohms.
ohms
Yes
are
or no?
parallel. Yes,
2
sir.
into 2 divided by 2 plus 2. That becomes 1 ohm.
1
Is that
more.
okay?
Yes,
Is that
sir.
okay?
Yes, sir.
So here also you can perform the same. Here it is minus plus, that is downward direction. Yes or no?
Yes, sir.
Minus plus or plus minus? Plus minus only. I'm sorry. No.
Okay, sir.
Okay, that I mean that will see. According to the polarity, you have to decide the current direction. If it is plus minus upward direction, if it is minus plus downward direction. So after
Okay.
getting this, now you can transform this into current source in parallel with resistance. You can transform this into voltage source in series with the same resistance. What is the value of voltage source?
3,
3 into 1, that is 3 volts. Here
3,
the value of voltage source is 3 into 3
3
by
by
4 into
4
1,
volts.
3 by 4 volts. The resistance is here it is 1 ohm, here it is 3 by
3
4
by
ohm.
4 ohm.
Now you can combine these two voltage sources. Yes or no?
Yes, sir.
Why? Because these two are in series. Plus minus, here also plus minus.
Plus minus.
Plus minus with 3 plus 3 by 4.
3 by 4.
That is 15 by 4. And 1 plus 3 by 4, that is 7 by 4.
Yes,
Again, you
sir.
can transform this into current source in
Current source
parallel
in
with the
parallel with resistance.
same resistance. The value of current source is I is equal to V by R. That is 15 by 4 divided by 7 by 4. 4 gets
15 by
cancelled out.
7.
Okay. So this
Okay,
is
sir.
how you can, perform source transformation. Okay.
Okay, sir.
Shall we continue or shall we stop here?
Sir, time is over, sir.
Okay. We'll continue next week.
Okay, sir.
Okay, just, we'll continue with the same topic. Then we'll move on to problems. Okay.
Okay.
Is this okay today's class?
Yes, sir.
Is it useful?
Yes, sir.
Have we learned any new points?
Yes, sir.
Okay, thank you very much. Madam,
Sir, if you can, please share the material.
Okay, definitely,
I pass
madam.
that
Madam, I will share with you. Just share with students, madam. Or else, madam,
yes, sir.
do one thing, madam.
Yeah.
Create WhatsApp group so that I will share in that.
Okay, you can send to me. I forward to group. No
Okay,
problem.
that is better. That is better. I will share to you.
Yes,
And
sir.
okay, thank you, madam.
If you
Thank
want,
you
you
very
can
much.
continue the class. Yeah, thank you. Right.
No, no, she said that time is all like that. That's why.
Right. Okay, right.
So,
Okay.
next week,
Thank you.
try to plan 10 to 1, madam. Why? Because it requires more hours.
Okay, right. Okay.
So
Uh,
next
okay, sir.
Sunday, I mean, if it is possible, 10 to
You
1.
want 10
Otherwise,
to
2 to. Okay,
Okay,
thank you,
sir.
madam.
Okay, for sure.
Okay.
Yeah.
Thank you, students. Thank you, madam. Thank you, madam. Bye. Okay. I'm
Thank you.
leaving.
Ma'am, shall we leave, ma'am?
Hello? Yes, you can. You can.
Okay, ma'am.
Thank you. Thanks a lot. Bye.